Welcome to qnawire.
For this problem, we have a particle that moving under a central force. And so the angular momentum per unit mass, h, is a constant. And so the definition of h, r squared theta dot, must be some constant h naught, which is equivalent to its initial position r naught times its initial velocity v naught. So if we rearrange this equation, we can find the theta dt, or theta dot, to be r naught v naught over r squared. And this becomes r naught v naught over r naught squared times cos 2 theta. So we're just substituting for r here. We have an expression for r. So we see the r naughts, one r naught from the top and the bottom cancel. So we get v naught over r naught times the cosine of 2 theta. So we have an expression for theta dot in terms of theta. So now if we differentiate r with respect to time, we get r dot. So r dot by the chain rule is dr d theta dt, or just theta dot. And this is equal to d by d theta of our expression for r, which is r naught over the square root of cos 2 theta. And this is multiplied by theta dot. So if we first perform this differentiation of the brackets with respect to theta, and then open our theta dot, which we have an expression for, we get that r dot simplifies to v naught times sine 2 theta over the square root of cos 2 theta. So that's a bit of mathematics. Now, differentiating again to find r double dot, we will see why we need this later on. R double dot is equal to d by d theta of r dot times theta dot. So this is equal to d theta of the expression for r dot, which is v naught sine 2 theta over the square root of cos 2 theta. And if we perform this derivation, well, this is multiplied by theta dot. If we perform this differentiation with respect to theta, and then again expand theta dot with our expression above, we get r double dot to be v naught squared over r naught multiplied by 2 cos squared 2 theta plus sine squared 2 theta over the square root of cos 2 theta. So now that we have r double dot, let's tackle part A. So the first thing we need to do is find Vr and V theta. So Vr is simply r dot, and r dot we've calculated already. So that's V naught sine 2 theta over the square root of cos 2 theta. And so this becomes V naught, so this is V naught sine 2 theta over the square root of cos 2 theta. So we can bring our expression for r into this. So we write this in terms of r to be v naught r over r naught times sine 2 theta. Remember, we have an expression for r in terms of theta. And so we have Vr. The transverse component of the velocity v theta is equal to r theta dot. And so this is simply v naught r over r naught times cos 2 theta. So we have the radial and transverse components of the velocity. So hence we can find the resultant velocity. The resultant velocity v is equal to the square root of Vr squared plus v theta squared, the square root of the sum of the squares of each component. And so this is equal to v naught r over r naught times the square root. We substitute all our expressions in here. Sine squared 2 theta plus cos squared 2 theta. And remember, sine squared theta plus cos squared theta is simply 1. So v simplifies to v naught r over r naught. So we've shown that the velocity of the particle v is proportional to r. And r is the distance from the particle to the center of the force at point O. So now that we have v, let's calculate the acceleration a. And a, the radial component of a, is the first derivative of the velocity v dot. So that's r double dot minus r theta dot squared. And so this is why we found r double dot above. So this is v naught squared over r naught into 2 cos squared 2 theta plus sine squared 2 theta all over the square root of cos 2 theta minus the second term is r naught over the square root of cos 2 theta times v naught squared over r naught squared times cos squared 2 theta. So if we simplify this with a bit of mathematics, we get this to be v naught over r naught times the square root of cos 2 theta. But we can write this in terms of r as v naught squared times r over r naught squared. So we have the acceleration in terms of r. And that's great because that means that the radial component of the force, the resultant force, Fr is equal to mar by Newton's second law. And then this is simply m, the mass of the particle, times v naught squared times r over r naught squared. So we have an expression for our force, and our central force is also directly proportional to r. So again, we've shown the velocity and the resultant force acting along the line of motion of the particle to be directly proportional to r. So now we need to go to part B to find the radius of curvature. So since the particle moves under a central force, we know that the tangential component, or the theta component of A, is equal to 0. And therefore, the magnitude of the acceleration A, which is the square root of AR squared plus A theta squared is simply the square root of AR squared, which is AR. And we've shown that this is V naught squared times R over R naught squared. So that's the theta component of the acceleration. Now, let's find the tangential and normal components of the acceleration. So the tangential component of the acceleration, A subscript t, is simply dv dt. So this is the time derivative of our velocity, which we showed is v naught r over r naught. And so this is simply v naught over r naught times r dot. Obviously, just the time derivative of r, since v naught and r naught are constants. And so this becomes v naught squared r over r naught squared sine 2 theta. So we just take the expression for r and find the first derivative with respect to time. And then the normal component of acceleration, we'll call it a n. An is equal to the square root of the magnitude of the acceleration, a squared minus the tangential component, at squared. And so if we perform this, we get this to be v naught squared over r, v naught squared times r over r naught squared times the square root of 1 minus sine squared 2 theta. And so this simplifies to v naught squared times r times cos 2 theta over r naught squared. So we have an expression for the normal component of the acceleration. But we also know that cos 2 theta can be written as r naught over r all squared from our expression for r. And this implies that the normal component of the acceleration, an, is equal to v naught squared over r. But v naught squared over r, the normal component, is also equal to v squared, the velocity of the particle, the final velocity of the particle, over its radius of curvature, rho. So this is actually part B of our problem, to find the radius of curvature. So if you rearrange this, we see that rho is equal to v squared over our normal component of acceleration, an. And so if we substitute our expressions in here, we get this to be v naught squared r squared over r naught squared multiplied by r over v naught squared. And so what we get is that rho, the radius of curvature, is r cubed over r naught squared. So we can see indeed that the radius of curvature of the particle's motion is directly proportional to r cubed.